Good morning, everyone, and welcome to Big Data. In the last week, we looked at the topic of bias in greater detail and formulated what a bias is. In supervised learning, it means that the distribution of your training examples is different to the distribution of your test examples. Big difference, obviously, these sets are always different, but here it's about the distributions. We saw how we can correct for a bias, but overall that doesn't really work because of the curse of dimensionality. We would need a lot of examples to reliably estimate these distributions. So rather, we make some discretion. And for example, for a class imbalance, which is a certain type of bias, we make certain assumptions, and then we can plug this in and solve for our bias or reduce for our bias far easier. Covariate shift is a different one, and such kind of biases are something you would notice, for example, through an exploratory data analysis. And here we make different assumptions, plug it into our weighting scheme, and it becomes at least a little bit easier to solve, still tricky when X is high dimensional. We talked about examples when biases appear. I also asked you to have a look at this survey paper that I wrote a few years ago, which provides you with more details on biases in AI or machine learning. And then we looked at small sample size problems that typically appear around biometric identification, CT scans, whatever. And there we may run into situations where models tend to overfit, where we have poor results. We know how to correct for this, but some models may even not be trainable at all when we don't have enough samples. And we saw this when we looked at linear regression and the normal equation, which actually then leads to a singular matrix. And we saw how we can address this by deleting features using the pseudo-inverse regularization. That's one example we looked at again in greater detail. Now, we started with uncertainty in learning, and today we will finish uncertainty in learning as well as the remaining chapters, since we have a double lecture today. And as of next week, we have phenomenal guest speakers for which I expect you to be on campus when we have on-site guest speakers. And as of, I think, tomorrow, you can also start picking your seminar topic. So this will open in iLearn. Do you already have some preference of which topics you'd like to explore in your seminar presentation? Maybe signal this with a positive or negative reaction, whether you have thought about your seminar topic already. You should definitely think about this very quickly because some topics may be gone very soon once the channel or once the iLearn portal opens tomorrow. Maybe just confirm whether, like, positive or negative reaction, whether you have been thinking about a topic already. So I see not many yet, but some, and hopefully the others will start choosing a topic soon, because as of tomorrow, you'll be able to choose in iLearn. We started looking at uncertainty in learning, discussed how we regularly evaluate hypotheses, and this gives us some insights, but it's actually not enough. And for this, we posed a couple of questions. And because these questions are so well answered in the Mitchell book chapter, I feel this is something that was great for you to read over the Easter vacation in the last few days. Because if there's a book chapter that just explains something extremely well, there's no need to turn it into slides, but rather just read the book chapter. A very good book chapter on how to evaluate hypotheses, and then these questions actually you know how to answer them. And that's what you need your confidence intervals and your statistical tests, in particular the pair two-sample t-test, but that one is also revised briefly in this book chapter. We also looked briefly into Gaussian processes, which give us also confidence intervals in their predictions, which is good, but the Gaussian processes, they have some pros and cons. And today we start looking into conformal prediction. We started with one slide last week already. So the beauty of conformal prediction is it's a very simple approach, in fact, and you can plug it into lots of predictive methods. In fact, predictive methods that work as the probability of the label given the data X. And the beauty of conformal prediction is it's a guaranteed frequentist coverage probability approach. And it allows us to create prediction intervals or prediction sets. And we don't make a lot of assumptions about the underlying data, like IID is something you would assume in lots of machine learning models. But this is all from the last century, and it's important stuff, but statistics is also involved. So the things that are now of more interest in statistics is distribution-free methods. So we don't make a lot of assumptions about the data. Here we only assume in conformal prediction that the data is exchangeable, means the order of the data doesn't matter. So the classic conformal prediction is something we would not be able to apply to time series, for example, but to all the other problems we know in supervised learning. Typically, exchangeability is something we can assume. So, but there are extensions of conformal prediction for time series as well. And I also refer to the famous Murphy book, which is now available as two books since 2 years ago. And the Advanced Topics book also covers conformal prediction. What I'm showing you here in these slides is just an essence of what the Murphy book actually presents when it comes to probabilistic machine to conformal prediction in the probabilistic machine learning advanced topics book. So what is the idea of conformal prediction? We are starting with a heuristic notion of uncertainty. So for example, we have a classification problem. Imagine, for example, a neural network, and a neural network has multiple output units. And what we want is we want a probability for in each unit, which refers to a probability in each class we are predicting. And in order to make sure that these are actual probabilities, typically what we use on the output layer of a neural network is the softmax score. For a revision, if you don't remember, the softmax score is, so you have all these output or all these values zi, and what you're doing, in fact, is you are raising e to the power of zi, where I is from 1 to k, so the k many outputs you have, and you divide it by the sum of every element raised to the power of that element, so e to the set j, where j is from 1 to k. And this is, so we raise e to every value we have in the output units, zj, and j again from 1 to k, and we divide e to the power of zi by that sum. And like this, we normalize these output scores so they sum up to 1. It's a very common approach to use this softmax score. And we use this one, for example, as a notion of uncertainty, but you can use others because these are always measures of uncertainty because all you get is probabilities. You're not guaranteed outputs. When you look at I don't know, regression problem, we could think about the variance. And we use such a score or such a heuristic to define a so-called conformal score. And the conformal score phenomenon is called S, and it has two inputs, the input vector X and the label Y, and that must be a real number. And this one measures, so the conformal score measures how badly the output Y conforms to the input or to the data X. So large values of the score are less likely. So we could better think about S as a sort of non-conformity score. It's always called conformal score, but in this context, we would rather interpret the conformal score as a sort of non-conformity score because large values of the score are less likely. We will see examples soon, then this will become more clear. Now we apply this score to a so-called calibration set where we have n labeled examples that we did not use to train our model F. So we leave some of the training data aside that we don't use, and we use this to build or keep a calibration set aside. So what we get is a set S where we store these conformal scores, which we called S, and we calculate these conformal scores for each of the elements from the calibration set. Because in the calibration set, we have labeled examples. So we have the example xi and yi as the corresponding label. We have n many. And what we are storing in here is these conformal scores, Si for the pair xi, yi. How to calculate these conformal scores exactly, something we'll see later when we look at examples, but we saw it can somehow be related, for example, to softmax or the variance or others. Now, you as the data scientist, you would specify a desired confidence threshold alpha, which could be, for example, 0.1. So when the book says the user, this does not mean the end user, but it's you, the data scientist, who builds this model. You would specify a desired confidence threshold, and we would then compute the 1 minus alpha quantile, which we call Q hat of S. When we use such a calibration set, this is often called in the literature a split conformal prediction. If you don't have enough data to do the splitting approach, we can also do something that the literature calls full conformal prediction. And that's an approach where you fit the model n times, where you use a leave one out type procedure. But for now, we just assume we have enough data so we can leave some of the data aside for our calibration set. But the literature also proposes alternatives when we don't have enough data to do this. So we compute the 1 minus alpha quantile Q hat of our calibration set S. And when you have a new test input, which we call X with index n plus 1, so one more, we want to compute the prediction set to be the following. We say T of our example, X index n plus 1, is the following. We calculate a prediction set where we say Y, or for that label Y, we calculate or we take all the labels for which the conformal value is less than or equal to Q hat. So because it's lots of new notation, I'm just going back to where we introduced it. So we said we have the conformal score, which is our real value, which we can also think about a sort of non-conformity score. And when we have a new example, we want to calculate the prediction set, and we take all the labels for which this conformal score is less than or equal to Q hat, which is our 1 minus alpha quantile of our calibration set. No, not lots of new notation, lots of new words. We intuitively would think we could. So what this means is, just in plain words, we include all the outputs Y, so all the possible labels that come from the model that are plausible given the input, because we have the conformal score and it must be less than or equal to the 1 minus alpha quantile Q hat of the calibration set. But we'll see examples soon, and then this may become more clear. What this means is something like this. Say, for a classification problem, say we have something like ImageNet, and our neural network, say, could predict 1,000 classes of some variation. So we have some variation of ImageNet where we have 1,000 classes. So our neural network would have 1,000 output units, and probably all output units will be some small values. Some values will be bigger than others, but probably almost none of these units is exactly zero. Because, for example, a monkey could still look maybe to like 1% like a dog, for example. There's maybe very small similarity, but not a lot of similarity. And that's why we apply this softmax score to normalize these outputs to make the likely ones more likely and the unlikely ones even smaller, but they're probably still not zero because of such a softmax approach. But what we did then is we take all the labels for which the conformal score is less than or equal to the 1 minus alpha quantile. And then what we get here is we would get, since you need to imagine the conformance score that we introduced before, the conformal score S, we said it's sort of a non-conformity measurement. So very large ones are the ones we want to ignore because these are not really conformal, because we need to imagine the S as a non-conformance score. So we would ignore the very large ones, and these are the ones that are under the threshold, that are less than or equal to our Q hat. And these are, so to say, the most likely labels that we get from this huge set of possible labels. And this is what we call the prediction set. And we can tune this by changing our confidence threshold. You can make it smaller or bigger. When you make it smaller or bigger, you can imagine what will happen. In one direction, you would include more of them. If you move it in the opposite direction, you would include less of them. And this is sort of a tuning task, sort of a hyperparameter of what you need to do experimentally in order to get a prediction set that actually works quite well for your use case. You can apply conformal prediction to classification. You can apply to regression. What this would mean in regression is you're predicting a value. And we've seen this last week when we looked at, for example, Gaussian processes. They gave us this confidence interval. And here what we get is a prediction set. So it's a different approach than the confidence interval, but still it gives us some set in which we are most likely with our value that we are predicting. And again, you can tune this prediction set. You can make it more narrow or more tight based on your use case. So it's a little bit related to the Gaussian process, yet a different approach. But from the visualization, you can get what we want to do is we have our regression and we need this prediction set of values that are actually most realistic. There is some more theory about conformal prediction if you take a look into Murphy book in case you want to study it, but I'm just leaving this out for now. What you need to know as a data scientist, you probably you don't need to implement conformal prediction from scratch. I'll show you soon how you can use this quite easy. Here are some more examples from a classification approach. So we use ImageNet, and what we do is we have an image and we want to have prediction sets. And what we see here are three progressively more difficult examples of the class fox squirrel. This one here is fairly easy, and the prediction set we get is only fox squirrel, which is the class. So this is one class, fox squirrel. Looks fairly easy, and for a well-tuned conformal prediction, this is what we would get. This would be the softmax score, 99%. Now, this image here looks more difficult because we have some more objects in here, like this bucket, and we have this tree, and maybe it's not necessarily a fox squirrel. And what we get is now in the prediction set, we get multiple possible classes based on how we tuned the alpha, yet this one here is still the most likely one. And for this example here, we see that the fox squirrel has a probability of 22%, but marmot actually has a 30%. So the right class here is actually not the topmost one, but actually number 2. We have a couple of more classes. And these would be these prediction sets, and these are the ones you can calibrate by working with your alpha. And if you want to try all of this out, you don't need to implement it from scratch. The good news is there's a library. It's called MAPI, Model Agnostic Prediction Interval Estimator. And this one implements conformal prediction for you. And you can easily plug it in into lots of models that come, for example, from scikit-learn, TensorFlow, PyTorch. And what you need to do is you need to import MAPI, and then whether you have a regression or a classification problem, pick the corresponding model. And you would then have, for example, a MAPI classifier, and your estimator, this would be the actual classifier, like say a logistic regression, maybe a tree or whatever, the models that would be allowed for which you have the probability of y given x. So only the valid ones you could plug in here, and then you could run conformal prediction, and you can just sort of easily plug it on top of your existing models. So this is something that is quite easy to use and gives you then sort of an uncertainty quantification on top of your model. Take a look at MAPI and the examples there. It's something quite helpful in case you want to build more reliable models. And now with ongoing regulation around AI, you need to spend more time on this. I've always been very skeptical when it comes to the AI Act because it comes with lots of unrealistic requirements. Yet you need to look into this kind of stuff now, and there's not just explainable AI, there's also uncertainty quantification and so forth. And conformal prediction is probably something that will become more popular in the next few years because of regulation. You need to look more into this kind of stuff. But building safe AI models that are reliable, this is not a future scenario. It's something you can do today. It's more than obviously conformal prediction. You need to look into biases and this kind of stuff. But we've seen plenty of this now in this course. And if you plug all of this together, you're definitely able to build more reliable machine learning models. So conformal prediction is one approach. There's another approach, which is called calibration. And this is something that has also become more popular in recent years. So the goal of, say, we now look at binary calibration is that we want to transform a score given by a machine learning model that is not a probability, and we want to transform this into a probability. We've seen the softmax score as one approach, but model calibration goes further. Concretely, the algorithms that we use for calibration, they can sort of be interpreted as estimators of the confidence level. And what we need to do is we need to fit independent and dependent variables to these models. And this is one example. The MAPI package that I mentioned here, it not just offers conformal prediction, it also offers model calibration. So it's overall quite a big and helpful package. And what we see here in this plot is the following. We start with the blue dots. There's some binary classification algorithm, and a model has, or we have trained multiple models, and they have an accuracy, as well as we have a confidence score for these models. And what we actually would like to have is we would like to have calibrated scores. So if we apply calibration, we would get scores that actually fit here on this linear function for which is x equals y. And this would be an outcome of calibration. What we get is that the scores predicted, they are closer to the true probability compared to the original output. So binary calibration is overall something very helpful because it gives us more reliable models. It turns out that even though deep learning is very popular, has become super popular, we all use deep learning now all day long. These very large neural networks that we use nowadays, they are far less calibrated than the old neural networks a few decades ago were. So in some sense, these new neural networks that we use now, they have a high accuracy, but in fact, their confidence has gone down and they actually have become quite unreliable, so poorly calibrated. This is something that was shown by a paper a few years ago, and just having high accuracy is not the only thing we need because we also need higher confidence. Um, and these deep neural networks that are so popular, they have very high accuracy, but less confidence. And you could try to calibrate these neural networks now, but this comes with new unintended consequences. I can only highly recommend you to follow Valery on LinkedIn. He's a very smart data scientist, very popular on LinkedIn, posts a lot of high quality content, and he works a lot on model calibration, on conformal prediction, also wrote a book on this kind of stuff, and posts a lot about reliable machine learning. And what he wrote about was he found a paper which showed that when you enhance calibration of models, this, at least with neural networks, when you enhance calibration of modern neural networks, and there are lots of methods to do this, like temperature scaling, entropy regularization, label smoothing, and others. Some of them are available in this MAPI package. Then you're increasing calibration, but you're reducing a critical element of performance, which is refinement. And refinement allows us to distinguish in a binary classification task. And this distinguishability is actually being reduced when you increase calibration. How to fix this, we don't know. It's an ongoing research problem. So if you want to learn more about reliable machine learning, model calibration, conformal prediction, take a look at Valery's LinkedIn. There's one more problem that can appear in machine learning, in uncertainty in learning. And this is, so we've seen various things now. We've seen conformal prediction, we've seen calibration, before we've seen biases. But one more problem can appear in reality. And that's actually that we have noise in our labels, not just in the inputs, but noise in the labels. Who of you has seen something like this when working with machine learning models? Maybe if you've seen something like this in a real world use case, maybe thumbs up. If you have not seen it, maybe thumbs down. So I just see if any of you has come across this in one of your real world use cases that you have worked on. So haven't seen that any of you has noticed this. Actually, noise in labels is a huge problem because we always assume that the label in our training data is sort of the ground truth, something we can ultimately trust. But now, these labels are not always correct. They can be wrong because experts disagree. They can be wrong because of some data processing issue. Lots of other reasons may cause noise in labels. And then you don't have this ground truth anymore. So you're actually learning wrong labels. And this is something that has been noticed in machine learning as an issue for the last 10 to 15 years. And there was a very fundamental paper on this, Learning with Noisy Labels, which appeared in the NeurIPS conference 12 years ago. Obviously, this topic and methods to address this have evolved, yet this paper is highly cited and overall quite helpful to read. I've seen noisy labels in lots of cases. For example, in, say, inspections. I've told you about my use case that I worked on, which was about detecting electricity theft. And there we also had noise in labels because maybe a thief stole electricity but manipulated the meter so well that the technicians did not find it. Or the thief removed the manipulation of the meter before the technicians actually came. So we got a wrong label. We got the label that there's no fraud, but maybe there was fraud. But we also suspected that the opposite direction could happen because the technicians, they also had to report a certain number of thefts every month. And maybe they didn't fulfill their quota. And they not only had to report like theft, but also, for example, broken infrastructure, malfunctioning meters. And if they had not fulfilled their quota, we assumed that sometimes they may just break a meter or somehow make it not work properly. So they report another broken meter. So we had a noise in both directions. And I've seen noise in labels also when it comes to quality inspections. Say you have output from a factory, and experts do disagree whether something is correctly produced, correctly glued, whatever. So when you collect such labels for your training data, you need to make sure that you reach some consensus among your experts because experts tend to disagree. That's quite tricky, but you need to do it. Otherwise, you're learning from wrong labels. And there are data sets like ImageNet, which have become super popular, but there have also been some studies arguing that a few percent of the labels in ImageNet are actually wrong because they were wrongly labeled by humans because you have tens or hundreds of thousands or even now millions of images in such a data set. Humans had to label this data set, and humans make mistakes. They click wrong, maybe they type something wrong, there's some data processing issue, and all of this can happen. And then you have wrong labels. And that's why when you see all these competitions now on ImageNet, someone trying to get better than others, say at 0.1%, I personally believe that all of this is quite useless. It doesn't lead to better models anymore because we have too much noise in the labels in these publicly available data sets. And if you just get 0.1% better on an imbalanced data set that is noisy, probably just a small improvement in the accuracy, from my perspective, doesn't lead to any reasonable conclusions. So pay attention to this. How do you detect noisy labels? Well, maybe in an exploratory data analysis, but there are also some statistical approaches that have been, for example, been proposed in this paper some years ago about how you could maybe try to build models that ignore noise in labels to a certain extent. So this is overall quite interesting work, and feel free to read this paper. I will not quiz you on all these further reading papers in detail after your seminar presentation, but you should read this kind of stuff since I guess you want to make a career in AI and machine learning and data science. So it's helpful if you possess some extra knowledge. And just 2 or 3 years ago, there's a very good survey that appeared, which is also called Learning from Noisy Labels with Deep Neural Networks, a survey, and it's quite an extensive survey about lots of different research that was done in this field, summarizing and contrasting some approaches, and appeared in one of the top journals, the IEEE Transactions on Neural Networks and Learning Systems. So feel free to read this paper too. Provides quite some reasonable insights on different approaches that address learning from noisy labels with a focus on deep neural networks. Now we have finished the uncertainty in learning. We have 2 smaller chapters left. So the ML Ops is something I asked you to read a few weeks ago because you should possess some knowledge about ML Ops when you pick your seminar topic. And since the portal will open tomorrow to pick your seminar topic, and most of the seminar topics are about these machine learning design patterns, and all of this addresses ML Ops, so machine learning and operations. Take a look at it. and this may help you to pick a more suitable design pattern. Now, in recent years, we see that these transformer models have become so popular. So I also want to say a few words about big data for NLP in this course, and some of the guest lectures we will have in the coming weeks and months. They will address more, also some of them will also address transformers and big data for natural language processing. So it's just a minor topic or smaller chapter I have here in this course, but I still want to share some of my thoughts with you on big data for NLP. Who of you feels that you're sort of okay, or you have some background in how transformer models work, or you have used them or tuned them? Maybe some thumbs up if you feel you have some background in transformers, or thumbs down if you don't think so. I'd like to see more responses from the students present. So overall, not too positive. I know it's some of the stuff that these kind of deep learning architectures will be also explored in the deep learning class. So I'll go a little bit deeper and start with some of the foundations. But you definitely had a natural language processing class that was taught like in your fourth semester, so 1 year ago. In the past, I taught half of the natural language processing course. So I taught this with 2 hours per week, and Udo Garman taught the other 2 hours per week with other stuff. But I just had too many courses, so I had to drop that half module. And now Udo Garman teaches the whole natural language processing module. Uh, so what we need to do is when we use a something like a transformer um, or not just a transformer, but other models in machine learning that work on text, we somehow need to think about how we can represent our text as numbers, because the machine learning models, including the transformers, they somehow they require us to turn our text into some format that they actually can process. And we can think about increasingly more complex approaches to do this. What we could do is we could assign a unique number to each word. So we could say the first word we find in a text is integer 1, then the next unique word we find is integer 2, and so forth. We could try to represent each word with a unique number. This overall does not work too well because this would lead to arbitrary distances and are difficult to interpret. So we have one word and another word, and say one is integer 2, the other is integer 2000, because it's number 2000 in terms of the unique words when I looked at them. So I'm creating arbitrary distances between these words. So that, say we have word X, or say word the is integer 2 and monkey is 2000. So the distance would be super huge, but if I just pick two other words like monkey and donkey, maybe they would have a much smaller distance. And these are all just arbitrary distances and difficult to interpret. So that's something we don't want to do. Never encode words with arbitrary unique numbers, because it will just lead to arbitrary distances that will severely impact your metrics and your training, and it will not lead to anything useful and will be difficult to interpret. A different approach is called one-hot encoding. One-hot encoding works the following. Say you have 10,000 unique words in your text. Then you would represent each word as a vector of the dimension 10,000, because we said we have 10,000 unique words. So for each unique word, we introduce one more dimension. And all entries in that vector are 0, except that one entry, that one dimension that refers to our word. For example, this is now a simple example here. We have 5 unique words in our text, which are cat, mat, on, set, the. And the would be one of those dimensions. So that word the would look as a vector like this because all the entries are 0 except that one dimension that refers to our word. For example, cat would look something like this, all entries 0 except the entry for the dimension for our word. And set would look something like this. This so-called one-hot encoding has a huge advantage. It's more interpretable because we can see each entry refers, or each dimension refers to a specific unique word. We can also see that we don't create arbitrary distances because all entries are 0 except that one dimension that refers to our word. So we don't create arbitrary distances, yet we create very large vectors that are extremely sparse. Sparse means largely 0, and concretely in each vector, only one entry has a 1. So it creates very sparse vectors that are extremely inefficient. We can try to store this in a slightly different format, and then it maybe needs less memory than storing the whole actual vector as is. Yet it's still a highly inefficient format and very inefficient to process, especially when we have very large texts. Each word will be represented by such a huge vector. And then what you would do, for example, is say you have a small text where you say the cat sat, and you want to represent that one text as a vector. You would say all entries are 0 except the entries for which these words appear. And then, so a few entries would be 1, and all the other entries would be 0. And with that one vector, you would represent your sample text. This is something that's been done for a long time in natural language processing. Say you have an email and you want to classify that email into spam or not spam. Then you would first go through all your possible words. So you build your one-hot encoding scheme, and then you take your emails for which you have a label, and you would turn the text into the one-hot encoding format. So you would see maybe from all your emails, you have 100,000 unique words, or from some dictionary, you would have 100,000 unique words. And then you have an email that came in that has 500 words. So you would set these corresponding entries in these dimensions to 1, and you have that one vector representing your email. What you lose is the order of the words, but you just store which words are actually in your email and which are not. And this would be the input to your machine learning model, and you would have to label whether it's spam or not spam. And this is how you would train a very simple spam classifier. And as the model, you could use a support vector machine, a logistic regression, maybe a tree model, whatever. Now, this one-hot encoding is inefficient, yet already better than encoding words with unique numbers. And there are two other approaches that we will look at now, which is word embeddings. Word embeddings have become super popular in the last 10 to 15 years because they're very efficient, very dense representations. They have something like this. Say we have a 4-dimensional word embedding, and each word in such an embedding would somehow be represented. So the word on would be represented by, for example, these values. It's not just integers anymore, it's now float values. And we have a 4-dimensional word embedding. And the interesting thing is these word embeddings are not defined by us. All we would define is the number of dimensions, for example, 200 or 500 dimensions. And we would pass a huge text sample to a model that would learn this encoding from data. Typically, this is done with a neural network. So we would not, by hand, try to encode words in our embedding space. Rather, the neural network will learn on its own an embedding representation for our words. And something that you will notice is that very similar words would have a very similar encoding. not exactly the same encoding, but a quite similar encoding. Why is that the case? Because when you learn these embeddings, what you take into account is not just the actual word, but its surrounding words, so its neighbors. And when you use that information, you can train with a neural network this embedding representation. And rather than using a very high dimensional one-hot encoding, we get typically a few hundred dimensions, and that would be a very efficient, dense representation. And very similar words have similar encodings. And this is a pre-processing step, like you have the one-hot encoding as a pre-processing step. And then you would have your words in this representation, and this is what you would feed into your subsequent machine learning model, like a transformer or something else. You can learn embeddings. For example, there are different approaches in neural networks where you can do this. For example, you can have a continuous back of words approach, or you can have these kipgrams approach. This is something that would be discussed in a more advanced natural language processing course in great detail. It is explained quite well in this new Bishop book that appeared 2 years ago, the deep learning book from Bishop that I also mentioned at the beginning of the course, which is called Deep Learning from Bishop and appeared end of 2023, early 2024. This one explains two approaches that are quite common, like back of words or this kipgrams approach, which help us to learn these embeddings. And we can look now at an example here. So it's just a simplified example where we use 4 dimensions. And for example, we see dog and cat, they differ quite a bit when it comes to these dimension, to these values. But for example, a cat and a lion, they are much closer. They are still 2 different words, and they are not synonyms, yet they are related, and so their embeddings are related. And all of this was purely learned from data. The neural network that learned this does not know what a cat or lion or tiger is, yet it was purely learned from the data, from the context, how these words appear together with other words. And we can see, for example, a mouse and a rat are quite similar, but yet quite different, for example, to an elephant. Now, in 4 dimensions, this is something still maybe not too easy to see. You could build a metric and try to see how different they are, but you can also try to visualize such data. So the data from before can be visualized in 2D. Do you know how to visualize a high dimensional data set in 2D? If you know, maybe thumbs up. If you don't know, thumbs down. And if you know it, maybe you can tell us how you can easily visualize a high dimensional data set in 2D. I'll see if anyone knows this. No, we don't have too many of our class today here because it's officially the lecture-free day, so we're doing this lecture online rather than on site, because we're starting with the guest lectures next week. So I didn't see from any one. So one thing you can do is PCA. You can do the principal component analysis. So PCA, I'm just sending this to the chat, is one approach. With PCA, you get the principal components of your data set, and then you could just keep, for example, the 2 largest components, and you could map like this your data set into a lower dimension. And then you can visualize your data set in 2D. One other approach is it's called T-SNE. I'm just writing it in the chat, and I'm pronouncing for those who are not in the chat right now, T and then hyphen SNE stands for T stochastic neighborhood estimation. And it's T stochastic neighbor embedding, not estimation. So T-SNE, T stochastic neighborhood embedding. Uses a t-distribution to find, also to map your data set from a high dimension into 2D or 3D with the particular focus on making this data set particularly nice to visualize in low dimensions. And there are obviously lots of other approaches that have been proposed for visualizing data in 2D. So for example, if you have your 4D data set, what you could do is you could apply t-SNE to it, or PCA, just keep the two largest components, and then you can visualize your data set like this. And what we see is we visualized the two principal components of word vectors that have 300 dimensions. And we see, for example, a cheetah, a lion, they are quite close, a tiger and a lion. Somehow elephant and lion are also quite close. Maybe they just appear together very often in this text. There's a big difference between a hamster and a cat, but a rat and a mouse appear quite close together. Pet and dog, and this is all just based on how these words appear together with other words in a large amount of text. And if you have a very large amount of text, you can learn these embeddings typically quite well. And here we try to visualize these embeddings, and we see words that appear close to each other are typically quite similar words. Yet in this data set, we see an elephant and a lion. They're quite different concepts, but maybe they appear quite often together in this text because the lion hunts elephants or whatever. Don't know if this really works, if an elephant gets hunted by a lion, or they just appear often together in this text. But these embeddings are overall super helpful because they're very efficient, dense representations, and it works overall far better than this one hot encoding. There's another approach that was quite popular in the past. Nowadays, it's lost some popularity, which doesn't mean it's irrelevant, but more people now focus on embeddings. The other approach is called TF-IDF, and TF-IDF stands for term frequency inverse document frequency. What you try to measure with TF-IDF is, so it's something you can just compute from a formula. You don't need a neural network to learn it. It's actually, you want to see how often words appear, or specific words, how often they appear, and in how many documents they also appear. And if you have, for example, a word that appears very often in each document, then it's maybe less, it provides less information than a word that only appears often in some documents, but not at all in other documents, or only very rarely. So this one may carry more information then. And this is something that TF-IDF tries to describe, and you can easily calculate your TF-IDF score of a word purely from the text corpus. So your text corpus would be multiple documents, and in each document you have words, and you can easily calculate these TF-IDF scores rather than learning them like a word embedding. And this would also be some pre-processing for each word that you would then feed into some subsequent machine learning model. So it's yet another approach. It works totally different than your word embeddings, but overall can be computed much cheaper. What you anyway would do nowadays is, if you have a new text, you wouldn't compute your word embeddings from scratch. Rather, you would use some pre-trained embeddings, and you would either use them as is, or you would fine-tune them a little bit. But these pre-trained word embeddings, they have already been calculated from very large amounts of text. You can just download them and use them, fine-tune maybe or maybe not, depending on your data. But overall, this is something you would typically not always just compute from scratch unless you have a very specific reason to do this. Now, what I notice is the field of NLP is moving very, very quickly. When I started teaching this course for the first time 5 years ago, there was a very interesting video. And this video is a presentation of one of my former classmates from my master's. So Marta studied with me. She later worked at DeepMind, one of the Google subsidiaries, and she gave a very good presentation just when COVID started on the then state of the art of natural language processing. So what was 5 years ago. And in that time, natural language processing focused a lot on sequences and processing sequences with recurrent neural networks. So a recurrent neural network allows us that we have recurrent connections and we can process time series data. These models were super popular, but a lot. So if you're curious about some great advances in NLP, that video is great. But just a lot of new stuff has happened in the last 5 years. And a lot of this goes back to a paper that was published in 2017. Attention is all you need. And this one proposed a neural network that looks something like this. So what is one of the big challenges in NLP? If we want to process text, or say natural language in general, what a lot of models would do is they try to learn how words appear together. So if you have one word, what is the most likely next word, and then the most likely next word from that sequence. And this is something that has been attempted in natural language processing for probably the last 50 years or something like this. And in the past, a lot of people did not talk about chatbots or NLP, but maybe more assistance systems that could answer certain questions. And something that was tried for a long time was building, for example, hidden Markov models. Hidden Markov models are one approach trying to learn how these words appear together. Technically speaking, it's not really words, but it's tokens. Maybe a small word is a token, or a token is a part of a big word or something like this, or some special character. And you want to know how tokens appear together. And this is something that was also attempted for a long time with recurrent neural networks, for example. But then in 2017, this attention is all you need paper was published. A major breakthrough in AI, as we know nowadays, and it proposed this kind of neural network. It's a high-level description. And what it offers is the attention mechanism. And the attention mechanism is a new approach based on neural networks that allows us to learn how tokens appear together. Now everyone talks about ChatGPT. ChatGPT is based on this because ChatGPT stands for Generative Pre-trained Transformer, and this right part of the neural network is actually the transformer. So ChatGPT is based on this right part of this neural network that was proposed now 8 years ago. And this paper has really massively changed NLP. I became aware, or I've started to look more into transformers since about the year 2020, because GPT-3, so the predecessor of ChatGPT, appeared in May 2020 and stands for Generative Pre-trained Transformer Model number 3. There was already a GPT-2 that appeared a little bit earlier, but I didn't follow this much. So I largely started to follow transformers as of GPT-3. And what it does internally is it uses this right part of the neural network to produce human-like text. And one of the versions that were GPT-3 was released in various sizes, but the most popular model was the one that has 175 billion parameters. And GPT-3 was trained on hundreds of billions of words, and it was noticed at that time that the training of such large models was already quite expensive. At that time, when you would try to train GPT-3 from scratch on a Tesla V100, which was the fastest GPU on the market at that time, it would take you with one GPU 355 years to train this model once. And this would cost you at least 4.6 million US dollars using US energy, US electricity prices when you, for example, use GPU cloud provider, like the cheapest one at that time would cost you 4.6 million US dollars to train this. So it was already noticed in that time that you would need quite a lot of GPUs in order to speed up the training, and the training was costly. And what was something very interesting about the GPT-3 5 years ago, so long before you enrolled into your AI bachelor's, it could not just generate text, but also source code or markup code like CSS, JSX, Python, and other stuff. So that's something that attracted my interest. And one thing I found very interesting about GPT-3 is the user interface offered more features than you have it now in ChatGPT. So you can use ChatGPT through the user interface, but you can also use it through an API. And if you use it through an API, you typically have much more parameters you can customize, something you don't see in the ChatGPT user interface. With GPT-3, all of this was in the user interface. And it's one of the reasons why it didn't become that popular at that time, because overall, such a user interface looks interesting to computer scientists, but not to the average user. And obviously, the model was not as good as ChatGPT is nowadays. But what you could do is you could have, for example, a text, and you could ask GPT-3 to summarize the text for you. And you could work with these parameters, like the temperature is something that would create or would increase creativity. You could customize the response length. So you could work with these parameters. It's something you can do now with ChatGPT only through the API, not in the user interface. And I experimented with some stuff, asked it to summarize some texts, do some question answering, asked it to suggest some blog topics. So all of this already worked quite well 5 years ago. I asked it to correct the language or the grammar of a text. I also asked it to improve or convert some Python code into, or reduce the size of Python code. So I had this loop and turned it into a list comprehension. All of this, all I noticed worked very well. For example, one of my friends at that time, he started a startup, and he needed to improve his website, but he didn't know much about JavaScript. So he used GPT-3 to generate lots of JavaScript for his website, and he amended it. So all of this worked quite well. And there was 5 years ago an initial hype around GPT-3 that some newspapers started using it. But that hype somehow disappeared very quickly because the results were not too great yet. And the user interface was also not that usable, but for the average user. You could also access it through an API. So all of this already worked. And then one platform that became more popular since then is Hugging Face, because it was noticed very quickly that you are unable to train your own models from scratch, at least not these very large language models, because it's just too expensive and you need too much hardware and we run out of electricity. And this is how Hugging Face became popular, because in Hugging Face, you can share models with others. They also offer some computing infrastructure if you want to train your models, and you can share models with others, pre-trained ones also. And then you can download a pre-trained model from Hugging Face, and you don't need to build everything from scratch. So it's something that became quite popular, and nowadays it's super popular. Then, end of 2022, ChatGPT appeared. And something I noticed around ChatGPT is it became super popular, not just because it returned or generated better results than GPT-3, but also the user interface was much simpler, much more accessible, and this definitely helped to reach out and make the average person use these tools. And you can use it also for coding, and you can generate easily a lot of source code with ChatGPT and now with other models as well. But it turns out when I asked ChatGPT 2 years ago, how can I train a transformer in Keras? What it actually generated is this kind of code. And if you use Keras, you will notice that this doesn't work because this library did not really work or exist in that way as we use it here. So it generated source code, but it just doesn't work that way. So something I noticed from these tools is they are very good in generating you whatever you wish, and the answers sound very convincing, but they are not necessarily correct. Now ChatGPT works better than 2.5 years ago, but yet it's still to be improved. And if you use it for coding, you can use it for coding and you become more efficient, but don't just trust it as it's generated. Still study the code well, test the code well, and so forth, because there may also be lots of security bugs in it. So don't just use what was generated and deploy it. Rather, test it well, study it well, debug it well before you put it in production, especially with regards to cybersecurity. I published last year a journal paper which describes in detail how these transformers work. The journal paper is called Technical Foundations of Generative AI Models. It appeared actually in some legal tech journal because lawyers told me they wanted to understand how ChatGPT works, because everyone is now talking about ChatGPT, but something I noticed, most people even don't know what GPT stands for, Generative Pre-trained Transformer. And that's why I wrote this 10 or 11 page journal paper last year. It appeared in early last year and provides an overview first about what is AI, what is deep learning, because the average reader may not know this. And then after this, I explain in detail various large language models and how this encoder-decoder framework we're using nowadays has become so popular, how internally you can train a model of that sort, especially a transformer. And I explain here in detail how the transformer architecture works. So I'm not discussing this today here in this course in detail, but rather you can also read this paper on the weekend or today in the afternoon, and you will see in detail how transformers work, some of the required knowledge in case you possess it. You can skip it, otherwise see it as a revision. I explain here the fundamental steps of training a transformer. There is, again, the Bishop book I mentioned, the Bishop Deep Learning book, and that one also explains well how the transformer architecture works. Something I notice is once you publish such a journal paper, it's quickly out of date, because now in the last year, obviously more things have happened. In particular, retrieval augmented generation has become more important. So RAG, it's something I didn't mention it here because early last year, RAG was just starting to become more popular. So this is one of the things, once you publish such a journal paper, very quickly it will not be up to date anymore, but yet the foundations of how such a transformer works has not changed. So feel free to read it. And the Bishop book that appeared end of 2023, early 2024, also explains in greater detail how the architecture of a generative pre-trained transformer works. Take a look at the book if you wish. Now, also a few words on how we can use this here at university. something I notice is a lot of professors are including computer science professors, are very skeptical about students using generative AI tools. And there are lots of ideas about how to regulate it, how to constrain you using it. A lot of professors don't allow you to use AI for your seminar paper or your thesis. When ChatGPT appeared, end of 2022, I was actually in my research sabbatical, which was a very good coincidence because in my research sabbatical, I actually studied transformer architectures. And then during that research sabbatical, ChatGPT appeared. And I saw directly how the number of users went through the roof and felt how I could address this here at university. Now, we as professors, we have a lot of freedom in how we supervise a thesis. Now, we can largely set the rules that the individual student needs to follow. So I felt rather than constraining or banning you from using these tools, I felt the students who are doing their thesis with me, they would not only be allowed to use these tools, but I would rather expect you to use these tools because a lot has developed. Because productivity has now gone up a lot. And I'm just honest, when I work on papers, for example, when I worked here on this journal paper, I too use generative AI. I write nowadays very early a disclaimer or a note and write that these tools have assisted me in writing a paper, in particular drafting some of the structure and suggesting structure, turning some notes into sentences. And this is, I think, the only way how we can stay competitive to use these tools, because until recently, everyone only used like spell checkers. Now we have Gen AI available to everyone. And I think if we ignore this at university, the only thing that will happen is that we are preparing today's students for tomorrow's unemployment. Because you need to use these tools when you work as a coder, you need to use Gen AI if you work as a civil engineer, if you work as an economist. So the best thing we can do is actually to integrate this into our processes at university. And we teach AI in our department. So you study AI and you take, for example, this big data course, but it wouldn't sound very convincing to me if you were then not allowed to use these tools in your thesis. Uh, has any of you already started working on your bachelor's thesis? And if you have, are you allowed to use ChatGPT or other Gen AI tools? Maybe if you're allowed to use them, green sticker, if you're not allowed to use them, red sticker. And the same would apply to maybe some of your seminar papers that you have this term or last term. So only getting red reactions, so you're not allowed to use it. So here are the news. If you do your thesis with me, you're not only allowed to use these tools, but I would even expect you to use them. And this is what I presented after my research sabbatical in early 2023. I presented this to my colleagues in our department council, and the reaction overall was not that positive, I have to say. There were even some colleagues saying that AI would disappear, Gen AI was just a hype, something we wouldn't need. But I think if we want to seriously teach AI, we also need to allow you to use these tools. And then while I couldn't convince my colleagues or got largely criticism, the Frankfurter Allgemeine Zeitung, so Germany's leading newspaper, they were quite interested in my approach. And I could write an article there 2 years ago and write why I think universities need to integrate AI and Gen AI in their teaching and not just teach about it, but to integrate it into every degree program. And there are obviously some rules if you do a thesis or seminar paper with me, because first of all, you're expected to use these tools. You It's not like I allow you, I rather want you to use them because your productivity will go up. Most students doing a thesis with me, they do very experimental AI projects. So you can use Gen AI not just for writing part of your thesis, but also maybe for your code, and you can generate more experiments. And it's something I've seen in the last 2 years, productivity among the students that use these tools when doing a thesis with me has gone up through the roof. Obviously, ChatGPT will not write your whole thesis, but rather it can help you to suggest some structure, get some ideas, turn notes into sentences that are actually readable, but you're still expected to amend, improve, and extend the output of the Gen AI tool. You're ultimately reliable for what you're ultimately liable and responsible for what you're submitting. So you would probably still have to critically assess all of this and amend and improve and extend the output, and always make sure that what you're submitting is actually correct, because some of the outputs of Gen AI tools, they may sound convincing, but they could be completely wrong. You also need to put references in there to support your claims. You can ask Gen AI tools to generate references. It works better now with these tools than it did 2 or 3 years ago, because if you ask ChatGPT 2 years ago to also add references, it may just make up references or even entire journals that don't exist. But now this works a little bit better, and there's not just ChatGPT, obviously, there's Perplexity and others. But still, you need to make sure that this reference not only exists, but that the claim that you're making is actually supported by that reference. And you may need to add more references. I also want from my students to write in their thesis which AI tools they have used and what they have done using AI, maybe just writing 1 or 2 pages. I'd be very happy about this. I don't require that you have in your appendix like a whole list of prompts and outputs, because then your thesis would just get super long. But at least you should explain how you have used these tools and which tools and what you have noticed. It may happen that these tools copy and paste, or they generate whole sentences that have already been written like this in the literature. So if that's the case, that would be plagiarism. So it's not plagiarism from my perspective, because you use what ChatGPT or other Gen AI tools have generated for you, but rather they have plagiarized, and so you are plagiarizing if you copy and paste this. So you still need to check your thesis for plagiarism and fix that. And now a lot of my students, they do their thesis with industry, and we have phenomenal industrial partners every year. But very important, when you use these tools, always read the privacy policy of these AI tools before you use them, and do not send any confidential data or trade secrets to cloud-based AI tools, because your employer will most likely fire you and make you liable for the loss, because you don't know what these cloud-based AI tools will be doing with your data. So there are various solutions. You could get a better license where you get certain guarantees from OpenAI or one of the other vendors. Not sure if they are following what they are promising, but at least you're adding some layer. Alternatively, maybe run your own model locally, either a small model on your laptop or on a server in your company. And you can get plenty of these models from, for example, Hugging Face. They may not be as good as ChatGPT, but maybe they're far more efficient, or you can fine-tune them or amend them with your own data, and then they maybe work extremely well. But you also keep these models internally, and you don't lose your trade secrets, you don't have issues with confidential data, potentially less issues with regulation like the AI Act and data protection. There could still be some challenges from a regulatory perspective. So just because it runs locally, that doesn't mean you're allowed to do whatever you want to do, but possibly you will have less trouble than if you run this in a cloud-based tool. So these are the rules that students need to follow when they do their thesis with me. And I drafted these rules end of 2022, early 2023, and I have not amended them since then because they proved to be quite stable. And this is what I wrote about in the article in Frankfurter Allgemeine Zeitung. If you speak German, feel free to read the article, but you'll also find it online if you wish, and you can put it in Google Translate or ChatGPT, whatever, to translate it. And I just argue that we need to prepare everyone, so not just AI students, but every student in every subject for the AI future. And the best thing is we integrate AI into our processes and we're just becoming far more productive. Something you may notice also, if you take courses with me, every year, every course that I teach, every year I'm adding a little bit more content, and every year these courses becoming a little bit more difficult. But why am I doing this? Because the tools are getting better too that you need to study. So when you studied 50 years ago, there was no web, and you had to go to the library and look up books and try to find the adequate statements in the books, which took quite long. Then the World Wide Web appeared and search engines, and search became much easier. And we started to have computers, so you didn't have to handwrite your thesis, but you can easily just type it and amend it. And now we have Gen AI, it's just another step. So productivity and efficiency is going up. So I feel we should also every year add a little bit more content to these courses and make them a little bit more difficult because your productivity is going up too. There's a question if there's a risk of losing track of fundamentals. Absolutely, there's a risk like this. But in order to use these tools properly, you still need to know the foundations. So if you don't know the foundations, you just have no clue if it makes any sense what these tools are generating. And I think you can only use these tools well if you know your subject well, if you know reading and writing well. So if you don't know language well, probably these tools won't help at all. It's a bit like a calculator. If you have an understanding of arithmetics, the calculator will prove to be very helpful. But if you don't have that understanding, the calculator will not get you anywhere. So you still need to learn the foundations. I have two little kids at home, 3 and 5 years old. I also need to make sure that they learn all these foundations because otherwise they are unable to use these tools at all. And you still need to know how to write a text without using AI. But once you have these foundations, we can add AI on top. And I've noticed my writing has become far better in the last 2 or 3 years because I too have grown from the tools, but I'm able to assess what the outputs are and if they make sense. For example, one of my new books is just appearing in the next few weeks, and I wrote a chapter about quantum computing. And obviously, I used Gen AI tools to help turning some of my notes into a proper structure and making some suggestions of how to write this. But some of the statements that ChatGPT generated didn't make any sense, but you were only able to notice this if you have some understanding of quantum mechanics. And if you don't have that understanding, the text may sound very convincing, but it's still absolutely wrong. But even my 5-year-old daughter and we use ChatGPT from time to time to generate some images, and it's fun. But still, we need to learn, or she needs to learn how to draw on her own, how to paint on her own without using these tools. But maybe there are some fundamentals that we don't need in the future. Like today, we don't need to know how to go hunting anymore because we just go to the supermarket. So maybe this is also some skills that are changing, that we learn new skills and maybe some fundamentals are not that important anymore. But when it comes to reading and writing and understanding the foundations of your domain, I don't think that we can drop this right now. And I don't see that this would be happening anytime soon, but we'll see. I don't know. The field keeps evolving. So these are some of my views on Gen AI. And if you want to study in detail how ChatGPT works, it's maybe something that could be discussed in your deep learning class, or feel free to read my journal paper here to get some of those insights, or take a look into the Bishop book, which covers extremely well how this GPT architecture works. Now, we will come to our last chapter in this course, which is about a totally different approach to deal with large amounts of data. We've seen now different big data architectures, we've seen parallelism, we've seen issues that can happen in big data sets, we've seen biases and uncertainty in learning, and we've seen NLP. Now we will look into quantum computing. And quantum computing is a totally different computational approach that has become more popular in the last few years. Who of you took the algorithms and data structures course with me? If you have, maybe thumbs up or thumbs down if you have not taken algorithms and data structures with me. It was a very diverse course, and some students, they do their first year somewhere else and then they switch here. So some have taken that course with me and some have not. So in the algorithms and data structures course, I provided an intro to quantum computing, but that was in your first year. So we will look into quantum computing again. So there will be some overlap with what you have seen in the algorithms and data structures course, but that was now a few years ago. So it can also be a revision. But then we will also contrast it a bit to some of the things we have done in this course so far, because quantum computers, they are highly parallel, far more parallel than any of the architectures we have seen in this course. And quantum computers are super interesting also from a machine learning perspective, because they, or at least theory indicates, that with quantum computing, we could maybe generalize much better in machine learning from smaller data sets and maybe be less impacted by biases. So this overall super interesting. But we will deal with highly parallel architectures, far more parallel than what we have seen so far. And we will start by looking at the fundamental units in a quantum computer called qubits. We will look at quantum logic gates, and we will look at quantum computers and quantum algorithms. I also teach an elective on quantum computers or quantum computing in the winter terms. So this elective took place last semester, and it's taking place next semester again. In case maybe some of you have taken it, I don't know when you take your electives, while others may wish to take it next term. All of that is possible. The elective is just extremely popular, and we have every year like 400 students that want to take it, and we have capped the number of students at about 100 because there are also seminar presentations. But overall, I'm very happy that so many students want to study quantum computing, and a lot of them get inspired either from the big data course or from the algorithms and data structures introduction. So what we need to know in order to take advantage of this chapter is you need to be okay with complex numbers. So remember that complex numbers, they extend the space or they extend the set of real numbers, because complex numbers have two components, A and B. A and B are real numbers, but a complex number is A plus B times I, and I is the imaginary number, and I squared would be -1. So it's something you're not able to do with the real numbers, but with complex numbers you are. So you extend that set, and we'll need them in quantum computing. And you also need to be okay with logic gates, like in classic binary logic, we have AND gates, NOT gates, OR gates, and so forth. And we have inputs and we get outputs from that logic. And what is now the idea of quantum computing? So in quantum computing, we want to take advantage of quantum mechanics in order to perform computations. And such computers would be called quantum computers. And this is a concept that was largely proposed in the 1980s. So to exploit quantum mechanics from a computational perspective. And in recent years, there has been more progress because we now have real-world quantum computers that can actually be used. They're maybe not that powerful yet in the number of units they have, but we're making progress. It's a very active field, and we will see how it develops, but I think in the coming decades, we will rather have more quantum computers than today. And so the best thing is to prepare you now for that quantum future. And as I said, I also offer the quantum computing elective, in which we study quantum computing for one whole semester and see a lot of the underlying calculations and architectures and how to program quantum computers. Today, we have maybe half an hour or 1 hour to at least look a little bit at that. And if you wish, you can try to take the elective next term. Did any of you take my elective already? I think at least one of the students, if I look at the names in the chat, I remember that at least one of them took the elective. So if you took it, maybe just signal this with some sign. But so far, I'm only getting negative reactions. So, and the interesting thing is quantum computers are highly parallel. So we are taking advantage of something called quantum parallelism. And that's why quantum computers are believed to solve certain computational problems much faster than classical computers. Important certain computational problems, not all of them. And significantly faster means in terms of a better complexity class, so not just a constant factor, but better complexity classes, because we take advantage of quantum parallelism. And this field has got a lot of attention in the last few years with regards to machine learning, but also encryption and decryption, in particular, cracking today's encryption. While all of this sounds super interesting, I am absolutely convinced that quantum computers will not replace all traditional computers anytime soon. I don't think this will happen in the foreseeable future. Quantum computers will rather address certain niche problems like encryption, decryption problems, certain machine learning problems, and optimization problems, but they will not replace all of our traditional computers anytime soon. So I'm convinced there will be a coexistence of traditional computers for which we have a combination of RISC and CISC architectures, and they are highly flexible. They can be applied to lots of computational problems very easily. And quantum computers address certain niche problems, and I think this is where quantum computers will also remain. They will grow. We'll have bigger and better quantum computers. But they will not replace all of our traditional computers anytime soon. And we are probably still decades away from very large, extremely powerful quantum computers, because the ones we have today, they are still quite limited. But we'll look also at some roadmaps later and see what big vendors actually believe how quickly all of this could materialize. So we have qubits, and the qubit is the basic unit of a quantum computer. Like we have in a traditional computer, a bit, which is either on or off. So in exactly one of the two states, a qubit can be in both states at the same time. So it can be in both 0 and 1 at the same time. So a qubit is also sometimes called a quantum bit. And this gives us parallelism. Concretely, we have, from a quantum mechanical perspective, a so-called superposition of the two basic states, 0 and 1, and we are in both with a certain proportion at the same time. And this gives us parallelism, especially if we not only have one qubit, but many qubits, as we will later see. So qubits can also be described in a mathematical notation. And what we use is the so-called bracket notation. So this here is called a ket, not like the pet, but ket is K-E-T. So this is from a physics notation of vectors, the bracket notation. And A is our qubit, which we represent, so a single qubit, which we represent as a vector. And it actually has a 0 and a 1 component. So we have the 0 ket and the 1 ket. And this vector, 0 ket, you need to imagine it. It's just a column vector where the first entry is 1 and the second entry is 0. So 1 and 0. While the 1 ket is just the opposite. It's a 0 and then a 1. So also a column vector with two entries. So the 0 ket and that 1 in the first entry refers to the 0 component, and the 1 here in the second entry refers to the 1 component. And we now need to put in the so-called probability amplitudes, which is sort of a proportion, how much we are in 0 and how much we are in 1. And we multiply the 0 ket with an alpha and the 1 ket with a beta. And I just told you before, the 0 ket is just a 1 and a 0, and the beta is a 0 and a 1. So if you multiply alpha with your 0 ket, that's just a 1. The 0 ket is a 1 and then a 0, so that would be just an alpha in the first entry, and this would be the beta in the second entry. Now, we cannot, so what is alpha and beta? These are the probability amplitudes, and this is where we need the complex numbers. Alpha and beta are complex numbers and so-called complex probability amplitudes of the qubit. And they need to follow a certain constraint. So we take the absolute value of alpha and square it plus the absolute value of beta and square it. And this needs to add up to 1. So sometimes instead of absolute value, I say modulus of alpha and squared plus modulus of beta squared. This needs to add up to 1. And only then when you have a valid qubit. And alpha and beta, they are complex values. This is something that is very important. And something I find very interesting about quantum mechanics is quantum mechanics, you can see it from a physical perspective. So maybe this is something you saw towards the end of your A levels, but you can also see quantum mechanics actually more like as a generalization of probability theory. And if you see it from that perspective, we can exploit it probably more easily from a computational view. So we don't care too much about the actual underlying physics. We more care that we have a more like a generalized probability framework. And this is something for which we can use quantum mechanics very well. So a ket refers to our single qubit. And we have an alpha and a beta entry. And it's just, you're using quantum mechanics. In quantum mechanics, you can have more than two entries, obviously, but we're constraining this now to 0 and 1. And now we have our qubits. Now we want to have multiple qubits and we want to do operations on them. And for this, we need so-called quantum logic gates. And what we need is, you need fundamental operations that our quantum computer can do. In a traditional binary computer, we have our fundamental operations not and or, and we want to combine them in order to calculate some logic function. And this is also what we want to do in a quantum computer, but we have different fundamental gates. One issue that we have in quantum computing at the moment is we oftentimes deal on a very low-level approach. So we work with these low-level fundamental operations. This is something that was also done in traditional computing. Like 60 years ago, people actually sat there and combined binary logic gates into higher level functions. And then as an abstraction layer, later software was added, so you didn't need to manually wire these units, but rather use software in order to add some customization in it. But with quantum computers, we have software, yes, but we are still on this very low-level approach that we need to think about the individual building blocks and how to put them together. And nowadays, we don't do this in classic software engineering anymore because we have high-level programming languages like Java or Python. So we don't need to think much about anymore how the low-level machine works because we have lots of abstraction layers in between. And in quantum computing, that's still quite limited. So we are on a very low-level approach when combining all these units. We'll start now with the most simple logic gate for quantum computing, and it's the NOT gate. It's actually quite similar to the NOT gate in binary computing. In binary computing, you flip a 0 to a 1 and you flip a 1 to a 0 with a NOT operation. What we are doing here is we have our qubit, which is alpha times 0 ket plus beta times 1 ket. And if I apply the quantum NOT operation, this one is often called X. And X we can see as a function, for example, and we would apply X to our qubit. And what we get out is, instead of alpha times 0 ket plus beta times 1 ket, we get a beta times 0 ket plus an alpha times 1 ket. So we're just flipping the amplitudes. And you can also see all of this not just as a function, but we can see this from a linear algebra perspective. So from a linear algebra perspective, what we can say is our vector alpha is, our vector A is our qubit, and the entries are alpha and beta. Now, with the NOT operation, we just flip them, and this is something we can also try with a linear algebra representation, because this X can be seen as an operator, and each operator in quantum computing can be expressed as a matrix. And what we do is we have our X, and X is an operator, so it's a matrix, and we can write it out as a matrix that is 0, 1, 1, 0, and we can put our X here now, which is just this matrix. And our convention for now is we have an operator, which is a matrix, and we multiply our column vector from the right. And this would be a valid qubit. These are the complex numbers, but for now, we only have a real component. We don't have an imaginary component of this of these complex numbers. And remember, the constraint was the absolute value of alpha squared plus the absolute value of beta squared needs to add up to 1. So 0.6 squared is 0.36, and 0.8 squared is 0.64. And this just the squared absolute values, they add up to 1. Now, this is a valid qubit where 0.6 is alpha and 0.8 is beta, and we multiply it with this matrix, and what we get out is just 0.8 and 0.6. So we have just swapped the two amplitudes. And this is called the X or the NOT gate. It's the simplest quantum logic gate. And there are more logic gates. What I told you before is we have a superposition. A superposition is that our qubit is partially in 0 and partially in 1. But when I have a quantum computer, which is some device that maintains a quantum state, I need to be able to access it from outside. And our outside world, I have binary states. So somehow, when I start my quantum computing algorithm, I need to be able to start the superposition, because I'm starting with classic values, and a classic input would be a 0 or 0 ket. It would be a qubit that is just in 0, or a qubit that is only in 1 of 1 ket. And I need to be able to transform such a basis state into a superposition. And one valid superposition would be something like this: 0 ket plus 1 ket divided by the square root of 2. This would be a valid qubit, which is a so-called equal superposition, because the equal superposition means it's half in 0 and half in 1. And I don't write a half here, but I divide this by the square root of 2, because the factor 1 divided by the square root of 2 applies to the 0 ket as well as the 1 ket. And then when I square this, then I have a half plus another half, and then it's 1. So I want to map the basis state into such an equal superposition, or the 1 into this superposition here. And this can be represented by the so-called Harder-Matt matrix, which is called H, and it's 1, 1, 1 minus 1, and it has this constant factor for each entry, which is 1 divided by square root. So feel free to do this at home as a homework, that you have your state 0, which is a 0 ket, which is a 1 and a 0, so a 2-entry column vector, and you would multiply this from the right with this H matrix. So you multiply the column vector from the right, and you can eventually notice that you would get this superposition. So this can be your homework trying to do these calculations. And you can also do it for the 1 ket, which is a 0 and 1 as the column vector, and you multiply it with the Harder-Matt matrix. Don't forget the constant factors, and you will eventually get something like this. This Harder-Matt gate is a fundamental gate because it allows us to create superpositions. That means we have parallelism, and then we can start working on these parallelism, or on these superpositions with other gates. And what we build is a quantum circuit. And eventually, in a quantum circuit, we will have different qubits. So here we would have 4 qubits, 1, 2, 3, 4, and we would feed in something. So we would start from outside just with classic values, which are all 0 in these qubits. And then we have different operations in here. This is, for example, called a C-not operation, a conditional not operation. It doesn't matter what these operations do exactly. They're just more fundamental operations. This could be some operation. Maybe this one here is a Harder-Matt gate to create this equal superposition. What exactly these gates do doesn't matter here. It's just some computations that they are doing. And eventually, I have my quantum state here. So I have 4 qubits that are in some states. And then this is a so-called measurement. And the measurement means I'm turning my quantum state, or I'm turning each qubit into a classic value, which is either 0 or 1. And this, again, is something challenging, because imagine I have a quantum state like this, 0.6 and 0.8. So this would be 1 qubit. And if I try to do a measurement, you would most likely expect it gives me a 1 ket, because the 0.8 amplitude is greater than the 0.6. And this may happen when I do the measurement, but if I run the experiment again from scratch and I measure again, it may give me a 0, because it's a probabilistic operation. And just because one of the 2 kets has a larger amplitude, it doesn't mean that I always get that when I do a measurement. So I need to run this experiment not just once. I need to run such a quantum computing experiment many times, maybe thousands of times. And then I would each time measure each qubit, and eventually I would have a distribution per qubit, or how the distribution of all the qubits together develops. And in order to get reliable estimates, what the most likely output could be, I need to run such a quantum experiment many, many times, not just once. So I have uncertainty in these measurements, but I have more uncertainties in here. Remember, this is a quantum experiment. It's not a classical experiment. And I'm using quantum mechanics. So these qubits, they will start interacting with their outside environment. It's something that I call decoherence. Decoherence means a quantum system, if it's not fully isolated from its outside world, it starts interacting with its outside world. So it's losing its coherence. It's a process we call decoherence. Now, you could wonder, could we fully isolate the quantum system from the outside world? Well, we could try, even if this was possible, which is probably not the case, but even if it was possible, then we wouldn't be able to interact with it anymore because we want operations. We want to be able to manipulate the quantum system in some way. So we need not perfect isolation. We need to find a trade-off so we can still access it from outside and manipulate it, but we want little decoherence. So this is a trade-off you need to make. If you want it to be very easily to manipulate from outside, that you can easily access it, yes, but then you also have very high decoherence, which you don't want. So this is one of the current research challenges in quantum computing, how to reduce the decoherence. Because if you have high decoherence, or it will lead to unreliable outcomes. And you have uncertainty again in the measurements. So you have uncertainty while running this because of the decoherence, plus uncertainty when you do your measurements. So you have uncertainty twice in here. And this is a problem. And this is one of the challenges in quantum computing at the moment. Now, a few more words. I talked about these quantum logic gates, like the Harder-Matt matrix, the NOT matrix, and there are many more fundamental quantum logic gates. For them, there's also a constraint. So each quantum gate is represented by a matrix, but not just by any matrix. Concretely, quantum gates are represented by unitary matrices. So what is a unitary matrix? A unitary matrix, or a matrix U, is unitary if, so there's an operation which is the adjoint. We will look at that very soon. So it's very important. This is not a transpose, it's the adjoint. So if I apply the adjoint to U, and the adjoint is often pronounced as dagger, so U dagger, I take U dagger and multiply it with U. This must be the same as U times U dagger, and that must be the identity matrix. Remember, the identity matrix is all 0 except the first diagonal, which is 1. And only operations that satisfy this constraint are valid quantum gates. Now, what is the adjoint? We will look at it. What we do is we have a 2 times 2 matrix with entries A, B, C, and D. And I take the adjoint, so I take the dagger operation. What this will lead to is, first of all, I take the complex conjugate of each entry. That's why I put the bar on top. The complex conjugate means I'm flipping the sign of the imaginary part, but I'm also changing the order of B and C. So B and C has changed. So in fact, what I'm doing is I'm taking the transpose of this 2 times 2 matrix. That's why I'm flipping B and Z. But I'm also taking the complex conjugate of each entry. And we'll look now at an example. If I have a matrix like this, the first entry is 6 minus 3i, next entry is 2, next entry is minus I, and then minus 2 plus 4i, and I'm taking the adjoint. First of all, in the first entry, I'm changing the sign of the imaginary part, because that's why I take the complex conjugate. So 6 plus 3i instead of 6 minus 3i. Same down here, which was minus 2 plus 4i. It's minus 2 minus 4i. Then I'm flipping the elements in the second diagonal because it's the transpose, so 9i and 2, and I'm also changing the sign of the imaginary part, so the 2 stays because it only has a real part, and the 9i becomes minus 9i. So this is the adjoint operation. And only for matrices where U dagger times U is the same as U times U dagger, and that both of them is equal to the unitary, to the to the identity matrix. Only then I have a proper unitary matrix, and only those matrices can be quantum gates. This matrix here definitely is not unitary. I've only applied the dagger operation to this matrix as an example. But it turns out if I take my Harder-Mott matrix, which was this one here from before, and I apply the adjoint to it and I multiply it with itself. So this was U, the Harder-Mott, or here in this case H for Harder-Mott, dagger times the Harder-Mott operation. This is the identity matrix. Strictly speaking, I still need to say U times U dagger, but you can test this at home. But you can also try this calculation here at home, multiplying these two matrices, applying the dagger to this one, which in fact doesn't change this matrix, doesn't make any change here. And you multiply this, you will get the identity matrix. So the Harder-Mott operation is unitary, and therefore it's a valid quantum operation. Now you're wondering, why do we need this constraint of unitary matrices? What we need, or why we need this, is the following. What we want to have is reversible computing. Reversible computing is something that you don't know from binary computing. Say, what is reversible? An operation that you can just undo is the NOT gate. In classic binary logic, the NOT gate you can undo because you just apply it to itself. But if you have an AND operation, you cannot just undo it. Undoing would mean that if you have a result of an AND operation, that from that result, you could infer what the inputs were. And this is something you cannot do with an AND or an OR gate. So this does not work. So your classic binary computing, as you know it, is not reversible, but there's a branch of computing that is called reversible computing, which aims that you're able to undo every operation. For example, say an increment is undoable because you increment an integer by 1 and you can just subtract it, so you're able to reverse this. And reversible computing addresses a branch in computer science in which all operations are undoable. And we need this in quantum computing as well, because something you will notice in quantum computing is when you have more complex circuits, sometimes you need to create more superpositions, but later you want to undo these superpositions. So you add more gates to create more superpositions. Sometimes this is necessary, but sometimes you have to undo it because it leads to too many superpositions and you need to undo it in that process. And that's why every operation that we use in quantum computing, every logic gate in quantum computing needs to be reversible so we can undo it. And that's why we require these unitary matrices. This is discussed in great detail in my quantum computing elective that we offer in the next semester in the winter. There are also recordings on YouTube from last year if you wish to watch them. So we'll discuss all of these operations and how to build bigger circuits in detail. But the good thing is all we need in the quantum computing elective is we need to know complex numbers, and we need to know linear algebra, and we need to know algorithms. And from that, we will build everything. So the theory may be tough, but you don't need much prerequisites. All you need is linear algebra plus complex numbers. And we will even do a quick revision of complex numbers as well as linear algebra, and then introduce concepts like unitary matrices and so forth. Now we have the theory, and now we want to run all of this on quantum computers because the theory started appearing in the 80s. Now we want to run it. I've mentioned some challenges in the real world is decoherence, because the quantum system will start interacting with its environment, which is not great. And I also told you that we cannot measure the quantum states directly, but rather we always measure, or when we do a measurement, we either get a 0 and 1, and when we repeat the experiment, we may get a different output. So there's uncertainty because of decoherence, but also because of measurements. And here we are really constrained by quantum mechanics, because if we measure a quantum system, we say that it collapses. And collapsing means the quantum system does not exist as such anymore, but we only have classic values, which are here 0 and 1. So once measured, the quantum experiment is over and we cannot just go back to it. So measuring destroys the experiment. That's why we only measure at the end. That's why if you have a quantum computer, you also cannot do debugging as we would do it in traditional computing, because in a debugger, you can look into your variables. But with a quantum computer, we cannot do this, because once we look at, or we try to look at what's inside, it will collapse and the experiment is over. So these are some challenges. We have decoherence and we have measurement, and now we need to build quantum computers that can run these operations. And this is something in which we are still limited today, but there has been some progress. For the last 10 to 15 years, an approach that is called quantum annealing, or adiabatic quantum computers, they have become popular, but they also face criticism because they are not universal quantum computers as we have seen them with our gates, but rather they use a different approach. And some people even claim that quantum annealing was not really quantum computers, but more like a different approach. So this is something that is being argued. But to date, the so-called quantum annealers, or adiabatic quantum computers, they are at least the ones that are most practical, the ones that have the most qubits, and they work a bit different to this universal approach we have just seen with the gates, but they're at least the most powerful ones today. All of this may change in the coming years, and we will soon look at these adiabatic quantum computers. Now, how do you get started? How do you run quantum computations? You can use a library like Qiskit. Qiskit comes from IBM. It's for universal quantum computers, not for quantum annealers. You could use them. They come with a simulator, so you can simulate a quantum algorithm or a quantum computer as an emulator in your traditional computer. But this only works for a very limited number of qubits, because once you try simulating this for lots of qubits, this is not possible on your computer anymore, so you need a real quantum computer. Now, how do you get a real quantum computer? We will look at the prices very soon. And for example, D-Wave. D-Wave is a vendor of these quantum annealers, or adiabatic quantum computers, which are this different approach. They sell different quantum computers. For example, they started selling a few years ago the 2000Q, and the 2000Q has 2048 qubits. So sounds a lot. If you look at IBM, they have quantum computers with maybe 1 or 200 qubits. Now, but they have universal quantum computers. IBM does not, D-Wave does not. D-Wave has a different approach, it's a totally different architecture. And these 2048 qubits, they are not interconnected. Just some of them are connected with each other. Now, there's a chip inside, and that chip is made of the metal niobium. And we want niobium to become superconductive. And for this, we need to cool down this quantum computer, or the chip, the inner part, to 0.015 Kelvin, which is close to absolute minus, which is around minus 273.135 degrees Celsius. Because what you see in here is not the actual computer. The chip is just a tiny piece, but you have a lot of hardware around it to cool it down to like 15 millikelvin. If you want to buy a D-Wave 2000Q, expect to spend 15 million US dollars on it, plus at least 1 million per year on the cooling. So it's expensive. But you don't need to buy one. If you sign up in the D-Wave cloud, you can run experiments for free. What you have in the cloud then is something like a Jupyter notebook in which you write Python code and you use a library that is offered by D-Wave in order to run these computations. Obviously, this Python code will not be run like this on a quantum computer. This will be run on a traditional computer, but you will have a few API calls to the quantum computer and some of its fundamental operations. And that part is run on the quantum computer or a simulator, and you get the results back. So you can run this on a simulator locally, or you run it directly with D-Wave on a real quantum computer. And what you get is like a free minute per month. I think meanwhile they have increased this, but it's only the running time of the experiment on the quantum computer. And that one takes maybe a few milliseconds. Like I did some clustering experiment, and that took like 300 milliseconds. And if you need more time, you can just buy more time per month if you wish. So you don't need to buy the whole quantum computer up front. This is how you can work with D-Wave as one approach. And D-Wave has, since the 2000Q, released more architectures. So that the 2000Q has more than 2000 qubits. We saw 2048. It provides some more details about how these qubits are connected. Concretely, in the 2000Q with a Chimera craft, that's one architecture of how to connect a few qubits together. And this is something that they released a few years ago, and that now there are new machines from D-Wave that the Advantage quantum processing unit has like more than 5,000 qubits, claims it's more than 10 times faster than the D-Wave 2000Q. D-Wave 2000Q uses a different technology. And now last year, the Advantage 2 has appeared, which has less qubits, but they are connected in a more complex way than before. So the effective qubits you can use in a calculation has gone up a lot. Now, why do we need so many qubits? In order for quantum computing to be scalable to real-world, large-scale problems, probably we need millions of qubits because we also have decoherence, we need error correction, and this kind of stuff, which also all needs qubits. And with thousands of qubits, we can only currently run like some toy problems because we are unable to interconnect all of them. If we were able to interconnect all of them and decoherence was not an issue, then this would work very well. Because imagine, I told you we have one qubit, which is in two states. Now, if we connect 10 qubits with each other, then we have 2 to the power of 10 many states at the same time. So with 10 qubits, if we interconnect them in full, we would be able to work on 1024 states at the same time. So massive parallelization already. So rather than going through one state at a time, we could apply our operations, so our gates, to 1024 states at the same time, which leads to massive parallelization. But they're not interconnected in this way, and this D-Wave architecture is anyway more constrained, but it's something that works okay nowadays and is probably the most practical approach. But there are other vendors, for example, IBM. And IBM has released this roadmap here a while back in which they write where they are right now. So, oops. So what they show here is in the year 2025, They want to reach a quantum computer that has 156 qubits. We can have up to 5,000 gates in there, while a few years ago they were down at 27 qubits. So this has gone up, and in the next few years they want to have more qubits and more gates. Obviously, there are some ambitious goals like up to 2033 to have 2,000 qubits, a billion gates. This is, as I said, the universal approach, which is far more powerful than what D-Wave has built. But it's a roadmap. It's to be seen whether all of this is realistic or not. IBM is working very hard on this. I was last year at a workshop together with the executive at IBM and IBM fellow who is in charge of the whole quantum computing work of IBM. And she and I hosted a workshop together in Switzerland, which was fantastic. So they are working very hard on this. Yet, this is not really just an engineering problem, it's a science problem. The IBM CEO says all of this was an engineering problem, not a science problem. I disagree here. It's a science problem because you need to control the decoherence. And for this, it's largely unclear to date how you could build such big quantum computers with thousands of qubits, a billion gates, while keeping the decoherence low. But we see they have an ambitious roadmap, and in 2 or 3 years, we can come back to their roadmap and see what they have achieved. They have achieved what they wanted until 2024. I don't know the old roadmaps, if there were also things that didn't work as expected that they had to delete from this map then. But in a few years, you can just come back to this roadmap and see what has been achieved and what they are working on at that time. So it's very exciting times. And for you, quantum computing will become more and more relevant in the coming years because there are also machine learning applications. And from the theory, it looks promising that we could learn maybe much more representative models from much less data, or we could do the training much faster on big amounts of data. And maybe we could also be less affected by biases in data. But this is something to be seen. It's just something that the literature suggests, which looks promising. In the next few years, we will see how this materializes. And maybe in 20 years from now, more of you will be training your machine learning models on a quantum computer. But these quantum computers, they also need to become cheaper, easier to operate, cheaper to operate. So we need massive miniaturization, but it's something we have always seen in computer science, that things get smaller and then cheaper, and we can scale them more. And this is something to be seen here. And there are lots of startups working on other approaches in quantum computing, like to have quantum hardware or quantum computers that run at room temperature, that have very low or even no decoherence. This is something to be seen. There are a lot of startups collecting funding ambitiously, and there are lots of promises. So let's see if these promises are going to be kept. But I want to prepare you for this quantum future. And now you may wonder how many quantum algorithms are actually there, because the theory sounds fantastic. And there's a very good website. It's called the Quantum Algorithm Zoo, which collects quantum algorithms that were published in the literature. And you find maybe 100 or something on this website. So there are about 100, I don't know the exact number, you see it on the website, of quantum algorithms that have been published in the literature. Now the question is, how many of them are useful? Most of them are probably purely academic, that solve purely academic problems that are not that relevant for real world issues. And there are, in fact, just a few quantum algorithms that have been proposed to date that actually have real world or useful real world use cases. We will study some of them now, but something that I notice is when you look at quantum algorithms and you study them, the ones described here in the quantum algorithm zoo, you would see that a lot of them have something in common. And most of these quantum algorithms, they have a few steps that are quite similar. So your quantum system will start with qubits in a particular classic state. This is what we had seen with this quantum circuit before. We start with zeros and ones. Then the system is put into a superposition of many states. This is something that would come next because we need parallelism in order to take advantage of quantum computers. So we need to put this into a superposition. Then, after we have the superpositions, we start working on the superposition where we have several unitary operations, these quantum gates we have seen before, and many more. So we do our operations, and finally we do a measurement. And then we would run this experiment many, many times in order to get a reliable distribution of the outcomes, because it's highly uncertain, both because of the decoherence as well as the measurement. But these are the typical steps of a quantum algorithm, and there are obviously variations. But this is still a general scheme that we probably see most of the time. I've mentioned all these challenges. We have decoherence, measurements, so it's all absolutely non-deterministic and quite different to traditional computing. And I want to discuss now a few quantum algorithms with you that have been proposed over the years that are, two of them are purely academic, and then there are two with real-world consequences. One, maybe the earliest quantum algorithm that was proposed by a researcher called Mr. Deutsch. He's not from Germany, but that's his name. What he thought about in the probably 80s was his work. So he studied such algorithms in the 80s and 90s. This first one here was probably from the 80s. What he wondered about is, so we have the following possible functions. We have a 0 and 1 input, and we can map these zeros and ones to 0 and 1. So one function could be that 0 and 1 are both mapped to 0. One could be that 0 and 1 are both mapped to 1. We could have a 0 mapped to a 0 and a 1 to a 1. And the last one could be we map a 0 to a 1 or a 1 to a 0. So these are the four possible functions when we can map 0, 1 to 0, 1. And now, if we have a function, we want to determine if it's balanced or constant. So we want to know, we have any of these functions, and we want to know directly with a quantum computer if such a function is balanced or constant. Balanced would mean that f of 0 is different to f of 1. So this one here would be balanced, and this one would be balanced, or constant, where f of 0 is f of 1. So these functions here, the first and the last one, are constant. And we want a quantum computer to determine this. So now I see it. This was proposed in 1985, and it showed that at that time, theoretical quantum computers that did not exist yet, that they could speed this up compared to traditional computing. It's a very simple problem, but a few years later, this algorithm was generalized as the Deutsch-Joscha algorithm, and now our function is more complex. Now the input is not just a 0 and 1, but actually we have many inputs that are either 0 or 1. And such a function maps this input either to 0 or 1. So we have an input of length n, which are zeros and ones, somehow spread or just random zeros and ones. And we want to map with this function that n long input to a 0 or 1. And here we want to know if the function is balanced or constant. And balanced here means if exactly half of the inputs go to 0 and the other half to 1, or constant means if all the inputs go to 0 or all the inputs go to 1. With a classical computer, this would be O of 2 to the power of n, if you try to solve this problem. But with a quantum computer, we could get an exponential speed up when solving this. So not just constant better, but exponentially faster. Still, however, a toy problem. This will be hardly used in real-world applications. And now we're coming to two algorithms for which there are real-world applications. One is the Grover's algorithm. And with Grover's algorithm, we address the following problem. We want to find, we have a black box function. So a black box means we don't know how this function works. And there are n possible inputs to this function, and exactly one of the inputs is the correct one that we want to find. So it could be some function doing whatever. It could be a machine, could return, different machine learning models, or it could be some internal calculations. We don't know. But all we want to know is we have n possible many inputs, and one of these inputs is exactly the right one that solves this problem. And black boxes, this black box approach could be applied to lots of different optimization problems. Now, with traditional computer science, solving this black box problem, so we want to find that unique input that is the correct one, is in the worst case in classical computing O of n. Because in the worst case, I need to try all n possible inputs until I have found the right one, which is the last one that solves this problem. Obviously, the best case is O of 1 if I'm just lucky with the first or one of the first few inputs to match the black box function. The average case is O of n half, but still we care about the worst case, which is O of n. And with classic computing, we are unable to get better than O of n. But with quantum computers, it turns out we can solve this in O of square root n. So we get, with quantum computers, we have the Grover's algorithm, which uses quantum mechanical phenomena to solve this black box function or black box search. And that algorithm needs about pi divided by 4 times square root of n many steps. So it's a squared speed up because it's O of square root of n. So runs much faster. But now I told you we need to run this experiment a few times because we get a result, and it's a non-deterministic algorithm. We get a result, but we still need to check if that's actually the correct result because it's non-deterministic and we have all this uncertainty. So once we have run the Grover's algorithm, we get some output and say the output would be or the result would be the correct input I need to put in. And then I still need to test it. And I need to put in that input into a black box function. I need to see whether the black box function says, yes, that's the correct input or not. And it may be wrong what the Grover's algorithm has returned to me. So I may need to run it again a few times until I get the right result. But probably just a few times at the very most, because overall the Grover's algorithm works quite well, yet there is uncertainty because of the computing environment. So I may need to do this a few times, yet it will probably run far faster when n gets large. So if n is 1 trillion and then the square root of 1 trillion definitely leads to a massive speed up, even if I need to run the experiment a few times. Now, the Grover's algorithm leads to a squared speed up, which is great, but some quantum algorithms lead to much better speed ups. And yet this quantum algorithm here that we saw, the Grover's algorithm, is highly generic. We can apply it to lots of different computational problems. Now, there's a very good website for you. It's called the quantum.country URL. And this one explains in detail how this black box search, the quantum search algorithm, works. It's a very interesting website. It's an interactive essay, so you learn new stuff, but next you also get questions and you get quizzed on. So this is overall really cool, and you can go through the essay, you can answer some quizzes, and then come back a few days later. You'll be showing quizzes again, and the website sort of stores whether you have performed well or not, and may give you the quizzes you had most often failed on. So it's a very good website, and it not only covers the quantum search algorithms or the black box search, Grover's algorithm, but also an introduction to quantum computing plus a few other selected chapters. So I can highly recommend you to look at this if you want to learn more about quantum computing. And the last algorithm for today is the Shor's algorithm. Today's encryption works very well because integer factorization is a computationally very challenging problem. So I have n. N is a very large integer, and I want to know what are its two prime factors. And because computing this is tricky, today's encryption works with very long keys, and we're very unlikely able to break that encryption because it would just take forever to run. Now, with classical computing, this would take an exponential amount of time. However, if you make some assumptions and you use, for example, a general number field sieve, then this runs in this complexity here, which is hard to read out. It's O of E to the whatever. Feel free to read this out on your own. This runs in sub-exponential time, yet because the general number field sieve makes some assumptions, otherwise this would run in exponential time, yet this would take extremely long to solve. And there is the so-called Shor's algorithm. It's a quantum algorithm that allows us to do integer factorization in polynomial time. And the Shor's algorithm has a complexity of O of log n squared times log of log n times log of log of log n. And this is in polynomial time, so the Shor's algorithm gives us an almost exponential speedup. However, we can only use Shor's for integer factorization, so we get a massive speedup. And here, the Grover's algorithm is a black box search that leads to squared speedup, which is not anywhere near exponential, yet already a massive speedup. And it's a highly generic algorithm we can apply to lots of different problems. We want to compare these four algorithms now. So they all address a different problem. But when we compare these algorithms, we can look at different properties. We can say one property is performance. And performance does not mean running time. Performance here means the algorithm solves a task well. Then the next property is speed up. So this is actually the speed that the algorithm runs faster than classical competitors, and not just by a constant factor, but really faster in terms of the complexity. The relevance would mean, is this problem actually relevant? Does this algorithm solve a real problem? And the last one is availability, that the technology to implement the algorithm could be available anytime soon. Now, if you look at the Deutsch algorithm, it solves a problem. So this was whether you have these four different functions mapping 0 to 1. Yes, it solves the problem well. It leads to a speed up, absolutely not relevant, but could be run on today's computers, quantum computers, or anytime soon. Same with the Deutsch-Joscha algorithm, solves a problem, leads to a speed up, and depending on the size of n, could be run on a quantum computer or anytime soon. Obviously, if n gets super large, then this is further away. But none of these problems is really relevant with regards to real-world applications. Grover's is different. it solves a task that is actually relevant, leads to a better complexity, but the question is, when is that available? We would really need bigger quantum computers with less decoherence, and we can interconnect more qubits. And then this could be run on an input of a or input function of a reasonable size. And it's the same with Shor's, solves a real world problem in a much better complexity, but when are these quantum computers available? And this is a big question that keeps, for example, intelligence and IT security companies busy. For example, the NSA and the CIA, they're actively working on this. So, because one day we have quantum computers that are large enough, we can just run a Shor's algorithm on the data and crack the encryption. That's why the NSA says they are storing everything they are collecting right now, also encrypted data, because maybe in 10 or 20 years they have a quantum computer that would allow them to crack this. But so far it's unclear when these quantum computers could become available. Maybe in a few years, maybe super far away, we don't know. Because it's not an engineering problem, it's also a science problem. This is something that is to be seen in the coming years, but IT security vendors are working on this. And now, last year, a couple of quantum safe encryption algorithms have been standardized because over the years, new algorithms were proposed that would be safe with regards to a quantum computer. So the ones that could not be cracked by a quantum computer. And there was a standardization process, and these standards are available since last year. And now IT vendors have started to implement these algorithms, and they're starting to deploy them. And you hear this, that Apple wants to deploy this to iMessage, and other vendors are planning to do the same now in the next few years, so that they are switching step by step to new encryption methods that are quantum safe. So when that big day comes, when these quantum computers are available, no one knows, could happen. Some people claim it could happen in the next 2 or 3 years. I disagree here. Probably it's much further away, but we don't know if there's some unexpected progress, that some new hardware gets developed that could work at room temperature with very low or no decoherence. We will see. And that's why IT vendors are preparing for this post-quantum encryption or quantum safe encryption, that when such computers are available, the encryption cannot be cracked anymore. So something we'll see in the next few years, decades, very exciting times. If you want to learn more about quantum computing, absolutely not for the seminar Q&A sessions, just if you're curious. I've mentioned this one here. I'm just going back. This website is phenomenal. Feel free to read it. There's also a book chapter. It's called Quantum Technologies. The Quantum Technologies Quantum Technologies chapter appeared in one of my books a few years ago. So a few years ago, I published a book which is called Innovative Technologies for Market Leadership. And Daniel Akenine, who is one of the CTOs of Microsoft, I know him very well, and he wrote a book chapter for one of my books and wrote about quantum technologies, which covers more than quantum computing, but feel free to read it. You also find this in Nextcloud without buying the book, so it's not a sales pitch. The quantum.country is very interesting. The D-Wave website is interesting. There are courses on EDX. There's a book on machine learning with quantum computers, which is very, very well written. And now a bit longer ago, Peter Widek, he wrote a book about quantum machine learning, and he offered this quantum machine learning course on EDX. And he was a real pioneer in quantum machine learning. Unfortunately, he passed away a few years ago. He went hiking and was hit by an avalanche, sadly. So we lost a real pioneer in this field, but you can still take, I think, his EDX course or read his book. There's now a newer book, The Machine Learning with Quantum Computers, that appeared a few years ago. So I hope some of these references are interesting to you, and feel free to read more about quantum computing if you wish. We have now finished the lecture part of this course. So next week we will have a guest lecture. Tristan Behrens will be on campus. We'll be speaking about transformers, but also AI agents. We are very excited about this, and I expect you to be on site for this guest lecture. We may be streaming, we may be recording based on whether we can record it. Let's see, and if Christian wants to be recorded, and we would expect you to be on campus. And then in the following weeks, we have more companies being on campus for the seminar presentations. And these companies, they're also looking for talent. So this may be interesting for you to get to know some companies where you could do your thesis, an internship, working student, or get a graduate position. I hope you got new insights into big data in this course. So we started with parallelism. We've ended with massive parallelism today. We looked at different architectures, different issues that can happen in data. We've seen uncertainty. We've seen machine learning in operations. And now the floor is yours to work on these seminar presentations and present them about 2 months from now. And in the meantime, we have a couple of guest lectures in the next 2 months. And I hope you learned lots of new stuff. Also, don't forget registering for this course together with deep learning in Primus. For deep learning, you have a separate examination. You need to do both examinations together this semester. Next semester, there's no resit because it's a seminar which we can only really run with a lot of students. So the examination is only offered next summer semester as well. And most likely I stop teaching this course because I have too many courses, and we have a new colleague, and she'll start most likely teaching big data next summer. Are there any questions from your side? If so, maybe send a green sticker, so I'll wait for you. If otherwise, if you now have no questions, send a red or different reaction. And with there not being any questions, I wish you a great remaining, actually lecture-free day. So thanks for tuning in today or watching the recording. So we have enough time for more guest lectures as of next week. Take care and goodbye.